Hello everyone, welcome to the lecture 13 in the course Diffusion in Solids. So today we will continue our discussion from the last lecture where we started talking about or rather revisiting some of the concept related to crystal structure and the defects in crystalline solids. So today we will be looking about some aspects of dislocations and grain boundaries, then certain defects in intermetallics and in the ionic solids. So, coming to one more point defect, which last class we talked about the vacancy, and we saw how we can determine the equilibrium concentration of the vacancies. It is called as equilibrium defect because it decreases the free energy of the crystal if present in a smaller amount, and so on. One more equilibrium defect is what is known as self-interstitial. So self-interstitials, they play a significant role, particularly when you have a radiation enhanced diffusion. That means self-interstitials, if certain radiations are falling on the material is exposed to radiations, then it is possible that self-interstitials, which is nothing but the parent atom itself moving to one of the interstitial sites. So these self-interstitials are formed. They are typically observed in some of the silver halides, AgCl, AgBr, and they exhibit this kind of a dumbbell configuration. And they are less common in metal. I will shortly show you why. But they are more common in semiconductors, which are actually less densely packed than metals and offer more space in the interstitial sites. And in fact, when you come to the diffusion in semiconductors, we'll also see that for them, there is not much difference between the formation enthalpies of self-interstitials and vacancies. And in some of the semiconductor systems, self-interstitials actually play a important role in diffusion. So, equilibrium fraction of self-interstitials like vacancies can be written in pure metals as Ci equilibrium is equal to Gi into exponential delta S IF by Kb into exponential minus delta H I F by Kb. So, this delta S and delta H are the formation entropy and enthalpy. Gi is a geometric factor which depends upon the crystal structure. For example, for FCC, it is equal to 3. Now, generally, the delta H for self-interstitial formation is almost 2 to 3 times more than the delta H for the formation of a monovacancies. Therefore, the thermal equilibrium at the thermal equilibrium, you will see that the vacancy concentration at equilibrium is much more than the concentration of the self-interstitials. So this therefore are in metals are more prominent when you have an external source like radiations falling onto your material, or in semiconductors we will see later that where the structure is more less densely packed rather, and therefore the self-interstitials can be more easily accommodated. So the next important class of defect in the metallic systems in particular is what is known as dislocations. So dislocation is a linear or a one-dimensional defect around which some of the atoms are basically misaligned. And all metals and alloys contain some dislocations that are introduced during solidification or during plastic deformation because of thermal stresses result from rapid cooling and so on. So invariably, all the metallic materials, they contain dislocation, nearly all. And the number of dislocations or the dislocation density in a material is usually expressed as total dislocation length per unit volume, or equivalently you can also say the number of dislocations that intersect a unit area of random cross section. And further, dislocation densities are usually as low as 10 power 3 per millimeter square in a very slowly, carefully solidified metal crystals. For heavily deformed material, it may also run as high as 10 power 9 to 10 power 10 millimeter per millimeter square. So dislocations, particularly when they are in a higher number, we will have a separate lecture devoted to that. That dislocation also act as a path for atoms to diffuse. So like we will see, the grain boundaries also are an important path for diffusion. Dislocations also are very important path for diffusion. So that's why it is better to know, or at least be familiar with the term dislocation and a few facts about it. So typically, the most important class of dislocation, there are two. One is edge dislocation. So you see, first of all, that this is what we mean by the misaligned atoms, or sometimes we say this is the extra half plane of atoms which is there. So you can see here there are 6 here, but on the above this line there are actually 7 these rows you can see. So this is a line defect. So this extends along this entire line which goes into the screen. So this is called as a edge dislocation, where every dislocation in fact is characterized by what is known as a Burgers vector. And in the case of edge dislocation, you can see, so this is the Burgers vector B. Okay, so basically this is the unit vector which tells you the misfit that is caused by the dislocation, and or in other words, the extra step that one has to take because of the presence of dislocation. So in the case of edge dislocation, you see that this is your Burgers vector, and the dislocation line is going into the screen. So therefore it is perpendicular, and that is the characteristic of a edge dislocation, where the dislocation line is perpendicular to the Burgers vector. The another type of dislocation line or dislocation is a screw dislocation, in which you see this is your Burgers vector, and this is the dislocation line. And therefore, in the case of screw dislocation, the Burgers vector is actually parallel to the dislocation line. So in reality, you will see that in the crystals, many of the dislocations have a mixed characteristic. So they have a certain edge component, they have certain screw component. So dislocations are a very important medium for the plastic deformation to occur in metals. So dislocation, both edge dislocation as well as the screw dislocation, the movement of dislocation is what contributes to what is known as slip deformation, or a plastic deformation by slip. And you see the step that is created on the application of the stress, shear stress tau. This proceeds by the movement of dislocation. So dislocations therefore are very important defects in materials from a mechanical property point of view. They influence greatly the mechanical behavior and so on. So, and as I told that they also have an influence on the diffusion characteristics. So typically, depending on the crystal structure, you have the Burgers vector of dislocation. The directions are different. For example, in FCC, it is A by 2, 110. In BCC, it is A by 2, 111. In HCP, it is A by 3, 112 bar 0. You might have noticed this is the close pack directions. So the next important defect, which is a 2D defect, is what is known as grain boundary. So grain boundary are basically, if you see in very simple terms, it is the boundary between the two grains which are oriented in a different way. So grain boundaries typically generate during the solidification. So there is a small schematic showing that you have small nuclei in the crystals, small nuclei which are growing inside your liquid, At the same time, there are several nuclei that are growing, and therefore, when they grow in random directions, they will tend to impinge each other. And when they impinge each other, then they form grains with irregular shape, and ultimately you have grains oriented in different directions, separated by grain boundaries. So this is another representation to show that the different grains can have different orientations, and the boundary for them, boundary between them, is what is known as a grain boundary. So each grain in itself is a single crystal, and within each there is a systematic packing of atoms, and as I said, they are separated by a neighboring grain from a grain boundary. So you can see this is another picture. So the extent of misalignment between two grain can be low, can be high. So therefore, these grain boundaries are usually classified as a high angle grain boundary, or a low angle grain boundary, or a small angle grain boundary. You can see here, for example, between this grain and this grain, the misalignment is not so much. So this is what is known as a small angle grain boundary, or a low angle grain boundary, whereas between these two grains, the degree of misalignment is more, and therefore it classifies as a high angle grain boundary. So typically, when the misalignment is between 2 to 15 degree, we call it as a low angle grain boundary. Beyond 15 degrees, they are termed as high angle grain boundaries. And you can see that within the boundary region, there is some disruption in the atomic arrangement as compared to the grain. So this is different from the crystalline orientations. Usually, the width of the boundary is typically 0.5 to 1 nanometer. So the high angle grain boundaries contain large areas of poor fit and have a relatively open structure. That's why, as I said, that they play an important role when it comes to the diffusion behavior, because they provide open channels for the diffusion to occur. And bonds between these atoms are broken or highly distorted, and consequently the boundary is associated with a relatively high energy. So there is a high energy associated with this grain boundary, and in the small angle grain boundaries, or in the low angle boundaries, because the misfit is less, so the energies are also less. A simple model of a grain boundary assumes just a stack of dislocations. So you can see here, this is a stack of edge dislocations which constitute basically grain boundary. And in that respect, you can see that the spacing between two edge dislocation is roughly estimated as b by theta, and therefore, so the d is equal to b by theta for very small theta. So actually, it is b by 2 sine theta by 2. But for very small angle, this can be written as theta by 2, and therefore it is equal to b by theta. So this is what I told, that the simplest grain boundary actually consists of configuration of edge dislocations between two grains. It is also referred to as tilt boundary. So this is a very simplified model, and actual grain boundaries are much more complex than what is actually depicted in this simple diagram. So the grain boundaries can be of various types. I've just given you this slide so that you get a little more information about the grain boundaries. So grain boundaries can be what is known as a tilt boundary. So you can see this is the two grains are tilted with respect to each other. You have this axis of tilt here. This is the axis of tilt, and this is the boundary. So this is called as a symmetrical tilt boundary. Means both the grains you can see are equivalent in all other aspects. There is also a twist boundary. So this you can see this when you are playing a Rubik cube or something. You can generate a twist boundary. Crystals are rotated about an axis normal to the boundary. So this is the twist axis, and this will at least contain two different arrays of screw dislocations. And then there is also this is a symmetrically boundary with vertical tilt axis. Then you can also have asymmetrically positioned grain boundary. The tilt boundary can be asymmetrical also. So these are different ways in which the boundaries can exist. They can be more complex than this as well. So it can be a combination of several things. Then the grain boundary energies, typically I mean, it is intuitive also that the higher the misorientation angle, higher would be the grain boundary energy. So you see that here at low angles, the grain boundary slowly increases till it reaches 10 to 15 degrees of angle, misorientation angle, after which it tends to become saturated. So usually the energy of low angle grain boundary is simply the total energy of the dislocations within the unit area of the boundary. This is just a schematic to show you. So here actually on the x-axis it is theta again, but this theta doesn't necessarily start from 0. What we want to show here is that these are the high angle grain boundaries, but at certain points you have a dip in the grain boundary energy, and that dip in the grain boundary energy is because of certain special high angle grain boundaries. Okay, so this special high angle grain boundaries, for example, twin boundaries, which have a mirror symmetry across the boundaries, although they are high angle, but they due to the symmetry, the energy is much lower. So there are certain special high angle grain boundaries which show lower grain boundary energy. Here is a thought question for you: do grain boundaries make the material strong or weak? So think about it. Usually it's an area of high energy. It's an area where atomic mismatch is there. But do grain boundaries make the material stronger or weaker? Then a couple of insights into what we known as intermetallics. I am sure you might have heard of this term if you have done any physical metallurgy course before, or in general also intermetallics basically are composed of two metals, or of a metal and a semi-metal. They usually intermetallics crystallize in ordered atomic distributions where the atoms are preferentially surrounded by unlike atoms. And some intermetallics are ordered up to their melting temperature, for example NiAl, whereas in some case there is an order disorder transitions with occur. So at low temperature it is ordered, at higher temperature it becomes disordered. Copper zinc intermetallics are one example here. And there are intermetallic which exist as narrow intermediate phase. There are intermetallic which exist as wider intermediate phase. That means they exist over a very small range of composition. Some intermetallic exist at for a larger range of composition, and we'll see in the lectures on interdiffusion that this range of composition actually also modifies or their diffusion behavior, or rather the composition profiles that are generated in such cases. So just here I have put some examples of this ordered intermetallic structure. For example, B2, where you have corner atoms occupied by one element, and the other element B is sitting on the body center. So this is known as a B2 ordered phase. NiAl, COAl, CuZn, AuZn are examples of these. Then you have what is known as L10 structure, copper aluminum. So you see that B atoms occupy these positions, whereas A occupies the corner and any one of the centers, phase centers, a pair of phase centers. And you see that here, unlike the disordered solid solution where any atom can sit anywhere, here it is not the case. So here B atom would like to sit only on this side, and A atom would like to occupy the other sides. This is L12 ordered phase. For example, Ni3Al, very important intermetallic, especially in superalloys. And you see that here the A atom is occupying the phase centers, whereas the B atom is occupying the corners. Then there are more complicated structures also. There are Laves phases, A15 ordered phases where A and B occupy specific positions. So when it comes to the defect in intermetallics, the defect in intermetallics are also, although there are vacancies which are also existing here, but because of maintaining the order, the defect configurations become more complex in the case of intermetallics. For example, one of the defect that is common in intermetallics is what is known as anti-site defect. You see that here. So what you should see here, blue and yellow in the perfect crystal is like two sublattices. So basically, you imagine this ordered intermetallic to be an combination of interpenetrating sublattices. So this blue colored is A sublattice, B is yellow color is the B sublattice, and intermetallic is a combination of these two. So now what may happen is that you may have anti-site defect. That means A atom is present on the site of B. So this is known as anti-site effect. So anti-site, that means something else is present on the site than it should have been. Then another important defect what you have in intermetallics is known as triple defect. In this case, you see here the triple defect means that there are two vacancies created on the A sublattice, and one of the A atoms actually occupy the B sublattice. So that means there is an anti-site also. So this is a combination of three defects, and it is therefore known as a triple defect. So you see in the case of this anti-site defect here, the composition becomes A-rich. Here it becomes B-rich. In a perfect crystal, it was actually equi-atomic, which is AB. So you can have anti-site on both the sublattices is also possible in the case of intermetallics. Another important class of crystals that we will see about diffusion in these crystals later in lectures when we talk about the specific systems. So this is what is known as ionic crystals. Ionic crystals, the ionic bonds I showed in the last lecture also, ionic bonds are usually much stronger than the metallic bonds, and here the Coulombic forces operate. And you see that here ionic crystals typically are also represented by two sublattices, cations and anions. And here the charge neutrality also needs to be maintained whenever we talk about the crystal structure or the defects or the diffusion. Also later we'll talk about. So the charge neutrality becomes a very important constraint here. So this is an example of NaCl structure. You can see that each Na plus ion is surrounded by 6 chlorine here, 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 and here. And similarly, each chlorine is surrounded by 6 Na plus, which is known as the coordination number. So there are two important defects in the case of ionic crystals. One is known as the Frankel defect. What Frankel defect means that from the cation sublattice, if the cation moves to the interstitial position, so that self interstitial is created, this is known as the Frankel defect. So you note that the charge neutrality is not disturbed because cation is not going anywhere. It is only moving from its own site, atomic site, to a interstitial site. So suppose if there are vacancies and self-interstitials in the cation sublattice, C sublattice is the cation sublattice, and they are formed from cations on cation sites. So then you can write Cc is equal to Vc, which is the vacancy on cation site, plus Ic, which is the self-interstitials of cations. So usually the equilibrium concentration of vacancy multiplied by equilibrium concentration of these self interstitial is equal to exponential delta SF P by Kb into exponential minus delta HF P by Kbt, where C equilibrium, Vc and C equilibrium Ic are equilibrium site fractions of vacancies and self-interstitial in the cation sublattice. That means how much is the vacancy here and what is the fraction of these self-interstitials. And KFP is known as the Frankel product. Okay, so here F and P it refers to Frankel pair or Frankel product, and this delta HFP is nothing but a combination of delta H vacancy formation plus delta H self-interstitial formation. You can basically imagine this, that first a cation has to be removed, so a vacancy has to be created, and then it has to be put into a self-interstitial. So there also energy is required. So this delta H and delta S can be written as summation of Vc plus Ic. And because the charge neutrality has to be maintained, so these two quantities should be equal. That means how many vacancies you create, same number of self-interstitials also have to be created, otherwise the charge neutrality will not be maintained. And if you put both of them as equal, you can write C vacancy equilibrium is equal to C interstitials equilibrium is equal to exponential delta SFP by 2 kb into exponential minus delta HFP by 2 kb T. So this occurs in the silver sublattices of AgCl and AgBr. And the one more important defect in ionic crystals, which is actually even more common than Frankel defect, is what is known as Schottky defect. In the Schottky defect, there is a simultaneous absence of a cation and anion. That means cation and anion vacancies are created together. This is known as Schottky defect. And Schottky disorder or Schottky defect, also the concentration product for vacancy on cation sublattice and on the anion sublattice can be expressed as exponential delta SFP by Kb into exponential minus delta HFSP by Kbt. So again here KSP refers to the Schottky product, and these are the equilibrium concentrations. So same way that because charge neutrality has to be maintained, so both the vacancy concentration needs to be equal, and therefore it can be written as C equilibrium Vc is equal to C equilibrium Va is equal to exponential minus delta HSP by 2 kb exponential minus delta HSP by 2 kb. Because the entropy term doesn't have minus here, so this is only plus. So delta SSP by 2 kb. So SP again is the Schottky product. So this occurs in many alkali halides like NaCl, KCl, NaI, KBr, and in several oxides as well. So thank you, and we will from the next lecture onwards start talking about the atomistic picture of diffusion, now having revised some of the concept of structures and defects. Thank you.